We would like to find an analog of Poincaré-Hopf theorem for the case of self-maps defined in a compact manifold without boundary. Okay, and indeed, in this lecture, we are going to introduce such an analog. It is called the Lefschetz fixed point theorem. If you have a self-map with isolated fixed points, this Lefschetz formula relates a topological invariant of your map, the so-called Lefschetz number, with the sum of some indexes that are analogous to the indexes of vector fields at isolated singularities at any of its fixed points. And this theory indeed is parallel to the one of vector fields, and these two formulas can be interpreted as just one. The Poincaré-Hopf formula can be seen as a particularization of the Lefschetz formula, and indeed we will see this more explicitly at the end of our lecture. We are going to see the connection between Poincaré-Hopf theorem and the Lefschetz fixed point theorem. So let F be a differentiable map from a compact manifold without boundary to itself. What we want is studying the fixed point set of F, okay? And more precisely, we want an analog of Poincaré-Hopf theorem, a theorem that allows us to calculate somehow the number of fixed points of F. So we are going to give a definition, the definition of Lefschetz number. Let F be a C1 map from M to M, where M is a compact manifold without boundary. And we define the Lefschetz number as the intersection of the diagonal, okay, the set of points, the submanifolds of the submanifold of M times M, whose points are of the form XX, where X belongs to M, and the graph of F, the points of the form X, F of X for X in M. These two sets are submanifolds of dimension equal to the dimension of M. And so they are submanifolds of complementary dimension of M times itself. Okay, so this intersection number is well defined, and by definition, it's the Lefschetz number. Let us point out that M times itself has a natural orientation in the neighborhood of the diagonal. Okay, suppose that omega x is an orientation of the tangent space of M at x. We can consider the product orientation of omega x with itself, and this is going to be an orientation of the tangent space of M times itself at the point xx. And if we consider now the orientation minus omega x, the opposite orientation, and the product of such an orientation with itself, then we get the same orientation. So in this way, we have an orientation of the restriction of the tangent bundle of M times itself to the diagonal. And indeed, we can obtain an orientation defined in the neighborhood of the diagonal, okay? So we are in a situation that it is analogous to the one we have for the tangent bundle. When we have a manifold M, the tangent bundle is not necessarily orientable because M is not necessarily orientable. But the total space of the tangent bundle, the tangent manifold, is always orientable, okay? And the situation is very similar to this one. It's because the restriction of the tangent bundle of the total space to M is isomorphic to the direct sum of the tangent bundle with itself. And here we are working in the product of the manifold M with itself. Okay, we can define the Lefschetz number for a continuous map. We are going to proceed as we did for vector fields by deformation, okay? It is an invariant up to diffeomorphism. Indeed, that's clear if the diffeomorphism preserves orientation, but it is true even if it's orientation reversing. Okay, if you have a diffeomorphism from M to M, for instance, this is going to induce a diffeomorphism from M times itself to the same space that sends xy to phi of x, phi of y. And when we consider the restriction to the diagonal, okay, this map over here preserves the orientation that we defined in the diagonal. Because if phi preserves orientation, here in the diagonal we have to consider that x is equal to y, but if phi preserves orientation, it's clear, and if phi reverses orientation here, it also does it here, so this map that we can call phi times phi always is orientation preserving. And essentially, because of that reason, the Lefschetz number is going to be a diffeomorphism invariant, okay? Of course, if the fixed point set of F is equal to the empty set, then the Lefschetz number is equal to 0, right? And in order to define the Lefschetz number for continuous maps, what we can do is finding a C-infinity map that is as close as we need to F in the C0 topology, and that is homotopic to F, and such that the graph of this F hat is transversal to delta. This is possible, and the way to do this is very similar to the case of vector fields. Okay. In this situation, we define the Lefschetz number of F as the Lefschetz number of F hat, okay, and we can actually also point out that the set of fixed points of F hat is going to be finite because of the transversality. We have to prove that the Lefschetz number is going to be a homotopy invariant, but this is because of the properties of intersection numbers. Okay. So what we want now is calculating indexes at fixed points. Okay. And let us start with the fixed points at which we have transversality. Okay, let us identify what transversality means. So consider a map, a C1 map from U to Rn, such that U is an open neighborhood of 0 in Rn, and 0 is a fixed point. Okay, then the diagonal is transverse to the graph of F at 0, 0, in the space Rn times itself, if and only if one is not an element, is not an eigenvalue of the differential of F at 0. Okay, and it is very easy to convince us of this. You have to think that the diagonal is the image by this map. This is a parametrization of the diagonal. We can also consider a parametrization of the graph. This is the map that is a parametrization of the graph. And we want to calculate the intersection number of the images of these two maps at the point 0, 0. Okay? But we can consider now the following map defined in Rn times Rn to Rn times itself that sends xy to xy minus x. This is a linear map that is orientation preserving with the standard orientations of Rn, okay, that induce a product orientation in R to M. Okay, but when we do that, xx becomes x0, and f of x becomes f of x minus x. And you are in the situation that we have for vector fields. This, you can interpret it as the zero section of this vector bundle, in which Rn is the base and Rn is also the fiber of the vector bundle. And we have to calculate the intersection of the zero section with this section over here. And in order to have transversality, we know that what we need is that the differential of this map at 0 is regular. So that 0 does not belong to is not an eigenvalue of the differential of f at 0 minus the identity, and so that 1 is not an eigenvalue of the differential of f at 0. Okay? A fixed point x of f such that 1 is not an eigenvalue of the differential of f at the point x is a Lefschetz point by definition. Okay? And a map f, a C1 map, is called a Lefschetz map if every fixed point is a Lefschetz point. Lefschetz fixed points are isolated, so a Lefschetz map has finitely many fixed points. And every map is homotopic to a C-infinity map of Lefschetz type. This is reminiscent of the property that we have for vector fields. Every vector field is homotopic to a C-infinity vector field that is transversal to the zero section of the tangent bundle. Okay, we have this lemma because we want to calculate indexes associated to fixed points, and we are going to consider a C1 map from M to M and suppose that X is a fixed point of F of Lefschetz type. Then we can calculate this intersection number of the diagonal on the graph of F at the point XX, and by definition that's going to be the index, the fixed point index of F at the point X. And it is going to be equal to 1 if this map, the differential of F at X minus the identity, which is a self-map of the tangent space of M at X, a linear self-map, is orientation preserving and equal to -1 otherwise. Okay, as we said, if we work locally, because this number over here just depends on the behavior of F at the neighborhood of X, okay, if we work locally, for instance, in X is 0 and a neighborhood of X in M is going to be a neighborhood of X in Rn just by considering local coordinates. What we saw is that the diagonal was parameterized by this map, and the graph was parameterized by this map, and that we consider an orientation preserving diffeomorphism that transform xx in x0 and xf of x in xf of x minus x. And we had a lemma for vector fields that says that a vector field of this kind that has a singularity at 0 is of positive type if this determinant is positive, if the determinant of the Jacobian matrix is positive. And that's what we're going to have here too. So it's going to be positive if this linear map is orientation preserving, and it's going to be -1 if this linear map is orientation reversing. Okay. This intersection number over here is called the fixed point index, okay, of the fixed point x, and it is invariant up to diffeomorphism. Indeed, if, for instance, you consider a matrix associated to this map, and then if that matrix is, for instance, A, we consider A minus the identity. What we get when we consider a change of coordinates given by a diffeomorphism, it's a similar matrix. And two matrices that are similar have either both of them positive determinant or both of them negative determinant. So the index is the same for a self-map and the conjugated of this self-map by a diffeomorphism, right? We get that the Lefschetz number of f, this intersection number between the diagonal and the graph of f, is just the sum of the indexes of the fixed points indexes of f at its fixed points if f is of Lefschetz type, right? But of course, we need f being of Lefschetz type. And here we have an example that we already considered when we were working with vector fields. And if we have a vector field, we are going to consider phi t, the flow of x in time t. And we are going to assume that t is positive and very close to 0. What happens then is that these flows, for instance, they're going to send this point to a point that is farther apart, but in the same half line. And these flows have exactly the same indexes as the corresponding singular points. So the index here is going to be equal to 1. The fixed point index here is going to be also equal to 1. Here it's going to be -1. Here it's 1, 1, 1, and here it's going to be 2. Okay, so we see that it looks like that there is a connection between the index for a vector field at a singular point and the fixed point index for a self-map at a fixed point. And yeah, we are going to explore this connection later on. Okay, now we want to extend the definition of fixed point index to isolated fixed points, as we did for vector fields. We are following the same program here. So consider an open ball D, which we can consider to be the ball of center at 0 and radius r, and a map F from U to Rn defined in an open neighborhood U of the closed ball, such that the unique fixed point of F in the closed ball is just the origin. Assume, furthermore, that the origin is a Lefschetz point, and we consider this map, the map that sends the boundary of the ball to Sn-1, and it's defined in the following way. Y is sent to Fy minus y divided by its norm. Since Fy minus y is equal to 0 if and only if y is a fixed point, and the unique fixed point in the closed ball is the origin, this is well defined, okay? And here, the fixed point, it's 0. We have that the index of f at 0 is the degree of g. This is proved in an analogous way as in the case of vector fields. Okay, and we have in this way an alternative definition for the index that we can extend now to the case of isolated fixed points, right? So let us consider the same situation as in the previous slide, but we are going to remove one hypothesis. Now the isolated fixed point 0 does not need to be a Lefschetz point. Other than that, the hypotheses are the same. F is a map defined in a neighborhood of a closed ball, and the unique fixed point in the closed ball is the origin. Now we can consider this map from the boundary of the ball to the sphere of dimension n-1 that sends y to fy minus y over its norm. And since there are no other fixed points other than the origin, this map is well defined because the denominator is always different than 0. In this way, we define the fixed point index of f at the origin as the degree of this map. Okay, and the definition does not depend on the choice of the particular ball. If we consider a ball of center 0 and radius s, and s belongs to the interval 0r, open at 0 and close at r, okay, we can consider for every s, the map G defined in the boundary of the ball of center 0 and radius s to the sphere of dimension n-1. And up to an obvious normalization, all these maps are homotopic up to a normalization because the domains of definition are not the same. But yeah, essentially all these maps are homotopic, and so the definition of the index does not depend on the ball. Moreover, we can actually check out that this definition of index is invariant up to diffeomorphism. And so we can use, if we have an isolated fixed point, we can use local coordinates to define the index, okay? Because the particular choice of local coordinates is not going to affect the definition because of this property. And now let us introduce the Lefschetz fixed point theorem. Let M be a compact differentiable manifold without boundary, and let F be a continuous map from M to itself with isolated fixed points. Then the Lefschetz number of F is equal to the sum of the fixed point indexes. Okay, this is clearly true if F is of Lefschetz type, okay, because it's essentially the definition. But analogously, as it happens for vector fields, this result can be extended to the case of isolated fixed points. In the case of vector fields, it's the case of isolated singularities. And we have this very cool theorem that relates this Lefschetz number, which is a global invariant of F, with this local data. Okay, now we are going to study the link between the Poincaré-Hopf theorem and the Lefschetz theorem. So consider X a C1 vector field and let phi t the t time flow of X. And what we have is that the Lefschetz number of phi t is equal to the Euler characteristic of M for any t. Okay, so let us see that the Lefschetz number of the identity is the Euler characteristic, because all these maps phi t are indeed homotopic to the identity map. In order to see this, let us consider X be a vector field, for instance, a C-infinity vector field defined on M, and such that X is transverse to the 0 section of M, okay? And what happens is that if we consider a very small t, the set of fixed points of the flow of X in time t is equal to the singular set of x. And this happens for t that is obviously different than 0, but small, okay? Moreover, we have that, that the diagonal is going to be transverse to the graph of phi t under this hypothesis over here, where it's going to happen for very small t. And something that it is very easy to show by working in local coordinates is the following. The index of the flow, the t-time flow of x at a point y is going to be equal to the index of the vector field x at the point y for every y. Again, for small values of t. Okay? And in particular, now, by using Poincaré-Hopf, we have that the sum of these indexes is the Euler characteristic, whereas by using the Lefschetz formula, we have that the sum of these indexes is the Lefschetz number of phi t. So we get that in this case, for small t, it's not difficult to prove that the Lefschetz number of phi t is the Euler characteristic. But since the Lefschetz number is a homotopy invariant, that implies that the Lefschetz number of the identity is actually the Euler characteristic. Okay? And in particular, the self-intersection of the diagonal in M times itself, which is the Lefschetz number of the identity, is going to be the Euler characteristic. And this is the way in which these two theories fit together. Indeed, we can see the Poincaré-Hopf theorem as a consequence of the Lefschetz fixed point theorem, okay? Moreover, any map F, any continuous map from M to itself that is homotopic to the identity satisfies that its Lefschetz number is the Euler characteristic, because F is homotopic to the identity, so its Lefschetz number is equal to the Lefschetz number of the identity, and that's the Euler characteristic. In the last few lectures, we have studied very powerful concepts, as for instance, the degree of a map, or the intersection number between a map and a submanifold, or the intersection number between two submanifolds of complementary dimensions. And we also saw results that relate global topological invariants of our manifolds with local data, namely the Poincaré-Hopf theorem and the Lefschetz fixed point theorem. For instance, Poincaré-Hopf theorem says that the Euler characteristic of a compact manifold without boundary is equal to the sum of the indexes of a vector field at its singular points, provided that the singularities are isolated, and that establishes a connection between global and local. For instance, we can use it to show that for a manifold that has non-vanishing Euler characteristic, every vector field has a singularity. But we can also use it in the other direction to calculate the Euler characteristic. Indeed, in our definition, the Euler characteristic is the self-intersection of the zero section of the tangent bundle. But there are other definitions in the literature, and they're all the same. And indeed, we saw a couple of these definitions for the case of compact orientable surfaces. Okay, by defining vector fields whose indexes were easy to calculate, we proved that if we have a compact orientable surface, then the Euler characteristic is 2 minus 2 times g, where g is the genus of the surface. And we also saw that if we have a triangulation of a compact surface, then the Euler characteristic is the number of vertices minus the number of edges plus the number of faces of the triangulation. Something that I would like to say is that a lot of the content of the course up to this point was intended to introduce the topics of the last lectures, degree of a map, intersection numbers, and so on. For instance, in order to define these concepts properly, we need to deform. But we need a rigorous way of deforming. And in order to do that, it was necessary to introduce a topology in the space of maps. Also, we need to know what we want as deformation, as a good deformation, what properties we want to get to. In general, the answer to this question in our case is transversality. And for that approach to be powerful, we need transversality to be a dense property. And indeed, if possible, to be an open and dense property. So we studied several topics that maybe it looked at some points a little bit technical, but I think that the payoff at this point is huge because these theorems that actually give to us global information of our manifolds are very, very cool. And we're just scratching the surface of differential topology. It is clear that the possibilities are endless. Thank you for your attention.